Hello, Mr. Eric, are you right? Okay. So remember we talked about breakfast search, breakfast search, right? Okay, so let's one easy graph. One A, B, C, D, E. Okay, so this is the graph. Undirected, yeah? Undirected. There's no direction, undirected graph, okay? And then what's the breakfast search order? If we start from A, this is the source.
A, B, C, D, E.
Well done. And we use the Q, right? Yeah, we push the look at the beginning we push the Q. Q equals A, right? The no, right? So we take a node A, we visit it. Yeah. Yeah, of course because it's a graph and we don't want to revisit the node B again once we visit it, right? So we take the A out, we check if we have a scene. We have a scene, yeah? We have seen. We have not seen A before, so we put this is the output, yeah? We visit it, and then we put A here. What's the A's children? B, C, D. We push the kids into it. We take the B out, yeah? Yeah? We take the B out. If it's not seen, right? We put it out, and then we put a scene here. What's the B's children? What's B's children?
B's children is E.
And because it's undirectional, look, undirectional. I'm visiting B, yeah, E and A, but A is already seen, right? Yeah, so we don't put it. But okay, so B we don't put it. There's a way we can check the scene, check if a node. We need to check if a node has been visited before we push it to the queue. So it's been visited, so we don't push it to the queue. So we only push the E out, right? And we take the C out. We take the C out. We put the C in here. What's the C's children? A, right? But we have visited here, so we don't push it, right? So we continue. We take the D out. And what's the D's children? What's D's children?
E and
A visited, so we don't put it, yeah. And A, we visited, so we don't put it, yeah. So let's put a D here, and then we take it E out, okay. So let's give us the order, and then we take E, A, B, C, D, E, okay. What's the depth search order if we start from A?
A, B, E.
A, B, E,
C.
and
D,
D, C.
C.
Okay. A, B, E, D, C. So to sum up, the breadth search travel level by level. So it always increase the distance, right? So when we find a C, we know it's the shortest distance, right? If it's an undirected graph, we know it's the shortest A to C or A to E, right? For the depth search, we explore the nodes until we count. Right? Look, we go to B, and then now I'm just trying to follow the road, yeah, B, yeah, to E, D. This is quite similar to traversing the binary tree. Yeah? We talk about binary trees quite a lot, right? A, B, C, D, yeah. A, B, C, D, E, F, G, right? A to B, and I can travel to D, and I go back to E, C, F, G. And the breadth search A, B, C, D, E, F, G. Okay. For the depth search, we use the stack, but usually we implement with the recursion and then let the computer to maintain the stack for us because we call it recursion, then computer have the stack, right? So the computer needs to push the call into a stack. Yeah. So define depth search. We are currently at current, right? So obviously there's a scene somewhere. We can put it in the parameter or here, right? So if current in scene, we just don't continue, we just return. Otherwise, for the node in G is the graph, yeah, current, and then we can depth search N, right? Yeah. And obviously we have to put it if we check the current if it's in scene, and if not, then we scene.add. Current. And that's the recursion, calling Excel, right? G graph, G is the a set of the vertex and the edge, right? So we can use the the vertex here, that will give us the list of the nodes, which, for example, A would be a list of nodes connected to A, which is B, C, D. This is the way to store the graph, which is called adjacent, right? ADJAC, adjacent list. Right? Because we can get the list of nodes, it connects it. Look, A connects to B, C, D. Okay, how about GB? So what does GB give us? GB. What's the GB give us? What's the nodes?
A and E.
Yeah, A and E. Okay, you get it, yeah? This is adjacent list. Adjacent metric is different, right? Adjacent metric is the metric. Right? So if you have a metric 1 0 1 0 0 1 0 1 0 0 1 0 0 0 1 1. Okay. This is adjacent metric. What does it mean? Look, this diagonal is always 1 because the diagonal, you can say this is A, B, C, D, and then this is A, B, C, D. If A and B is connected, you put a 1 here, right? If A and B is not connected, look, C and A is not connected, you put a 0, right? So you basically look it up, right? So if there are n vertices here, so this space complexity is O(n) squared, right? Yeah, look, you just look it up. For example, D to B, C is 1. Okay, can you explain to me why this diagonal is 1? It's always 1.
Because there's diagonal is like AA, like BB.
Yeah. So it's Excel, right? It doesn't matter. Actually, you can put 0. It doesn't matter because it just means that the node is it's a node Excel. It does not represent an edge between two vertices, right? It's basically a vertex. B to D, right? You look it up. D to B. So look, if this metric is mirroring by the diagonal, what does it mean? If it's mirroring. The mirroring, you know the mirroring? What if it's mirroring? If this is 0 and the diagonal here is this is also 0. If this is 1, this is also 1. What does it mean? Think about it. What does it mean?
It means like if you do BD either way, they'll be the same.
Yeah, it's undirected, right? If it's directed, if you look A to C, but C does not point to A, so A to C could be A to C here is 1, C to A here. And 0, right? Okay, well done. That's good job. That's adjacent metric, adjacent list. Okay, so now we want to visit the breadth search. Okay, breadth search. Define breadth search source. We use the Q equals DQ. Yeah, remember we use the DQ. Put the source in, and then we have scene equals set. By the way, what's the advantage of using DQ instead of list?
Because list, if you're gonna look up in the list, in the list it takes O(n) time to look up.
And but for this Q, we don't need to look it up. We need to do what?
We need to do stuff and
append. It's O(1). Pop from the left is O(n), right? But for the DQ, it's always to O(1) in both directions. Okay.
Yeah.
So while Q, and then we can say current equals Q dot pop left. Yeah, and then we can just say for node in G current, if n not in scene, and then we just Q dot append n, right? Yeah, and then obviously we need to put it scene dot n, right? This is the breadth search, right? Breadth search for graph, the data structure, the template, yeah, the algorithm. Q, DQ, scene, YQ, right? We put the source in the Q. We take the Q, we pop it from the left as long as the Q is not empty, and then we push its kit if it's not being seen to the Q, right? Yeah, look how simple is that, right? Okay, so one question. If I change this Q to stack, yeah,
you wouldn't able to pop. left.
Good question. That's a very good point. But I changed this to pop, just pop. You know the stack, first in, last out, right? Yeah. So what will happen? Does it become a DFS?
Not really.
Not really. Okay. Yeah, your answer is right. But let's look it. So the depth of search is what? A B E. Okay. The depth of search is A B E D C, right? Right? Yeah. But if we pop it, if we're using the stack, so if I push it to the right, so this is the stack, yeah? I put it A, I take it out, A, and I put a DCB here, DCB, right? The sequence is A. Okay, and I take a B out, right? Yeah? And then I need to put it, what? Put the E, right? I take the E. Take an E.
You're just putting it and then getting it back.
Yeah. Look, because I already visited, it's not V sin, right? This is sin equals A. I take it, I already visited, sin equals A, right? And I push the kids DCP, let's put it in the reverse order. I take it back, take it out, I take it out, and I push it to kid, which is E. A I already visited, so I don't push it. Okay, I take a E out, yeah, and I push the kids, which is D, already push it. So, already push it, I don't take it, right? So now I take a what's next? C, right? Yeah? So C. A, B, okay, so A, B, E, C, D. E, C, D, look, E, C, D. Which is different than A, B, E, D, C. You see the difference? The depth of search is A, B, E, D, C. But if I change this DQ to a stack, yeah, I emulate this for you. The sequence is A, B, E, C, D. It's different, right? It's not. So breadth first search, if we change the queue to stack, it's not actually the same as depth first search. Okay. Yeah. Okay. Okay, so this is just a side note. Okay. One question: the depth of search, is depth of search guarantee a shortest path? You know the shortest path. If I want to visit the shortest path between A, C, B, this is the triangle. I want to visit the shortest path. I want to calculate the shortest path from A to C. What's the shortest path? Undirected. Okay, let's talk about undirected. What's the shortest path?
A to C.
Yeah, okay. But for the depth of search, it might come this first, yeah? A, B, C, right? Once you found the node, it's not guaranteed the optimum, right? Yeah, it's not guaranteed the optimum. It's like the tree. A, B, C, D. It's not optimal. Okay, so if I can do this E, F, okay, G, okay, and then I have this another H. Okay, how about I have another G here? Another G here. Okay. So look, if you do the depth of search, you find the G. I want to find the shortest between A to G. You do the depth of search, you quickly find this, but it's not the shortest. It's not a guarantee, right? Get it? Because there's a path here which is shorter. Makes sense? So the depth of search does not guarantee the shortest path unless you visit all the paths from A to every other, yeah?
Which takes a long time.
Brute force it. Because look, if I extracted all the search to all other nodes, and I can compare, get the minimum, right? Make sense? But for the breadth of search, it's always guaranteed. Again, I'm talking about undirected graph, okay? The shortest path, look, A, B, E, C, D, F, A, H, G. Okay, I found this G here, not here, right? Make sense? But there's a way to change. Okay, this is the part of today. There's a way to change these DFS to breadth search, to guarantee a shortest path. There's a way. We are adding a maximum depth, depth, yeah, limit, or we call it depth limit. Depth limit. What does it mean? Look. Okay, let's travel with the maximum distance 1. The depth of search. So what does it give us?
A.
A. Okay, this is A. What? And now, okay, let's increase the depth to 2. What does it give us?
B and
E. Okay, A, B, A, E. Okay, we still haven't found the target. Let's increase one more time the target to 3. This, yeah? Yeah?
that's kind of like breakfast search.
Not really. Breadth search is like you travel nodes by nodes. But now I'm saying that I want to do the depth search with the maximum distance up to 3. So I can do this A, B, C, D, E, F. It doesn't go any further. Once we hit the the distance, we stop, right? And then we can increase to depth 4, right? Depth 5, okay. So in this way, we can find it. Is it faster or slow?
It's like the same as breakfast.
Not really. Okay, that's the difference. Breadth search for each node here, B, is visited once, right? But look, if I increase the depth for depth search, look, when is the distance 2, I visit the B. When is distance 3, I visit the B again. A, B, C. When I increase one more depth, A, B, C, D. You see? I repeatedly go over the depth search again and again. Okay? Make sense? So look at, the only difference we added for the depth search is to what? DEF depth search with the node current, but we have a maximum D. We add a this. So what is it? So what? First of all, if CUR in scene, we still return. Yeah? We are visited it, then we return. And then we visited scene current, scene.add current, yeah? Scene.add current. Okay, and then now I added this is one more, okay? If D, okay, so this D is the maximum D, and then we also need the current D, current D. This D is the maximum you can go. D is the current depth. So look, if D bigger than D, then we return, yeah? We just return. Because we have currently we are limiting our search distance to maximum 3 steps. But now we are traveling too far, so we stop. And then this is the other thing is the same, yeah? For N in GCUR, right? And then what should we do now? We travel DFS N. This is D never change. And then look at D. I need to do what? What should I do with D? What should I do with the D? The depth. If I visit one more node, what should I do? Plus what?
Plus 1.
Well done. Yeah, plus 1. Look, this is the only difference. This is the only difference with the normal depth. And then for the y, then we can say y not found. Yeah, not found. The found at the beginning equals none, right? Not found. Yeah. Then we can say, look, depth search found equals depth search. This D. We can start with the source. The D, and then at the beginning is 0, right? Or 1. It doesn't matter. And then look. And then what should we do? We should increment the D plus equals 1. Right? Yeah. This is to increase deepening. We call it iterative deepening. Iterative deepening. Deepening means that we perform the depth search with the depth D, and if we won't found it, we allowed it to have one more maximum distance, right? So we increase the maximum D one more, right? Until we found it. So look, as we said, the nodes. Okay, so the nodes with the depth A, and then the search distance if it's D, it needs to be visited how many times? Look, this is A, okay, this is B, this is C, this is D. Okay, now if I want to travel from A to D is the shortest distance, right? So this B, how many times it needs to be traveled? How many times it needs to visit? Okay. A, not visiting it. B, AB, visited 1 time. A, B, C, visited another time. A, B, C, D, visited another time. So you look, the nodes needs to be visited. Some nodes will be visited 1 more time, right? So look at this distance is 1, 2, 3, right? Right? And then this distance is 1. So So the nodes needs to be visited. 3 minus 1 plus 1, okay? So look, this is D, this is A, if this the distance is A, and how many times it needs to be visited is D minus A plus 1, okay? Make sense? Yeah? So, it looks like, okay, we have repeatedly visited a node. It might be slower, right? Yeah? Alright? It might, but there's advantage of using this iterative deepening. Look, if a tree, remember this binary tree, yeah? If it's a perfect, if it's a perfect binary tree, not perfect, we call it what? Full binary tree, yeah? Full binary tree. Full binary tree, every node, every layer, every node except the leaf node. This is the leaf node, yeah? Which all have 2 nodes, 2 children, right? Yeah? Look, if this D equals, the depth equals 1, 2, 3. How many leaf nodes are there? How many nodes in depth equals 3? 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, 8. So it's 8 actually 2 to the power of n, right? Yeah? Okay? So for the preferred search, we need to, the space complexity, look, we're talking about space complexity, needs to store all these. Yeah? Yeah? Alright? So the space complexity is exponential for preferred search because we are expanding all the nodes. All the nodes, right? Could be exponential. I'm talking about the full binary tree. Yeah? For the deepening, iterative deepening, I don't need to store all these nodes, right? I just need to store the depth. Yeah? Yeah? So let's say, it's the space complexity is less than this. Right, look, I just need to use the stack to store once the path, right? Yeah? I don't need to store any other thing, right? Yeah? Make sense? Yeah? Any questions so far?
Not really.
Okay, answer me. What's the advantage of iterative deepening and breadth search? Which one?
Because for the breadth search, you can, so you're like,
Oh yeah.
I'm here, so like, okay,
I need to put the kids of the same level, yeah?
same level, same
But for the full binary tree, this could be exponential, right?
yeah,
Is that?
meow,
Okay, you become bigger. Always
I'm
double,
never
yeah?
stopping, I'm never stopping,
Yeah.
so big and fat.
Okay. But for the iterative deepening, every time I try one more step, okay? Let's see if I can find this node with the maximum distance one. That's like that. I can't, then I increase the step to 2. I can't, step to 3. So for the depth search, I don't actually need to store all the nodes for the same level, right? I don't need to use a queue. The space I need to use for the depth search is stack, which stores what? The path is this bit, right? Yeah, ON, right? Yeah? ON, this is ON, and this is O2N, right? So the space, iterative deepening, is faster than not the speed. I'm talking about the space. Space used by the depth search is less than the breadth search in terms of, in some graphs, right? And for for some complex algorithm like min-max tree, or play chess, yeah? The chess. I play one. I want to get the chess. Usually 2 players. Yeah, it's like you play a chess. I take one. I move one step. You move one step. So look, I want to maximize the score like 100, and then you want to minimize the score, right? So you take one step, and then I take for the odd layer. I want to maximize. For the even layer, you want to minimize. Yeah, because each one take a turn, right? And then for this, in this kind of chess playing algorithm, usually we use the iterative deepening to allow us caching some states. So it's actually faster than breadth search. Okay, in some case, okay, yeah. It might be a bit too complicated, but Okay, what's your most important takeaway today? I talked about a few
It's
things.
about the different search and breadth search.
And what's the new concept we are talking about? With the D, what's this?
Is the deepening thing.
So, okay, so what's this bit? The last question, what's this bit?
If D is big, if like if we okay we're just visiting some few novel nodes, and if it's bigger than we saying if it's and like this part is saying this if we haven't seen it we get added, and this is if it's bigger and we just
And then if not, what's this bit? If not, we visit the next one using recursion depth search. But why is this D+1 here? What's D+1?
D+1 is
What's D?
D is the kind of deepening thing.
What's DIS distance?
Distance.
It's the distance. I visit one more node, the distance will be +1. And then I check if the distance exceeds the threshold, max threshold. If it exceeds, then I stop. Okay, I don't go further, right? Okay. So for this one, it's iterating deepening. Let's say I want to visit A to A. Look, the depth search, right? A, B, C. AC is not optimum. But if I say, okay, let's visit A with the step 1, A, B. AC, okay, I visit C. Because from here, B, I don't continue. Because it exceeds the threshold, right? So look, the pure depth search does not guarantee a shortest path because AC is the shortest path. If you do the pure depth search, it will go from A, B, C. This is not the optimal. But if I added the depth, and then at the beginning, let's start with one node, A, B, AC, I found it, right? Because A, B, I can't continue. Why is that? Because it exceeds 1, right? This is the distance 1. If I go here, that will be distance 2, right? And that will be returned here. It doesn't go continue. Look, make sense? Okay, that's it for today. Good job. Bye bye.
Bye bye.
Bye bye.